Hi, I'm Sosa, and we're going to be talking about the lipid bilayer today.
This is a phospholipid bilayer. As you can see, it's constantly in motion, up and down, left and right, in 3D lateral motion. This constant movement allows for glucose nonpolar molecules through the membrane, like hormones and gases.
Here we have the phospholipid. Basically, we have the fatty acid nonpolar tails, and then we have the polar head. Notice here that we have two other polar heads interacting with this polar head by polar interactions. Basically, this is what holds the matrix together, these polar interactions between the polar heads. This is the reason why the phospholipid matrix is an exergonic reaction, why it happens naturally when you put them into solution. Alright, this is the polar head. Notice your functional groups within here. You have the phosphate up here and the glycerol down here, which may comprise of carbonyls, and the R polar group over here. Here you have the two fatty acids. These are both non-polar because they comprise completely out of carbons and hydrogens. And this is the maximum degree of saturation. As you know, when it comes to calculated drawings, there's two hydrogens at each kink here for each carbon. As you remove hydrogens from the fatty acid itself becomes unsaturated, which means there are more double bonds or even triple bonds within the carbon-hydrogen molecule. This creates kinks, as I'm going to show you here, that take the entire fatty acid and kind of twist it out to the side. It creates more space between this phospholipid and the next phospholipid next to it. This more space allows the whole entire molecule to be more fluid and permeable. This is a cholesterol molecule. Notice the two hydroxyl groups on it. The strong polar interactions between the polar group and hydroxyl groups of the cholesterol allow the cholesterol to align polar to non-polar with the phospholipids. This allows for a firmer phospholipid matrix. Basically, it's less permeable to random polar molecules. This is a diagram of the lipid bilayer. Notice the transmembrane protein we have here. What's interesting about the transmembrane protein is that we have both hydrophilic and hydrophobic parts. Basically on the ends, where it aligns with the polar heads of the phospholipids, it interacts with water and it interacts with the other phospholipids next to it because it's also polar. But on the inside, which interacts with the fatty acid chains, is non-polar, and this is what stabilizes the transmembrane protein within the matrix. Here we have three phospholipid bilayers at room temperature. What we're trying to figure out here is which is going to be most fluid-like at room temperature, and which is going to be most solid-like at room temperature. For example 1, we have a bilayer with a lot of kinks in it, a lot of double bonds. Basically, it's long non-polar tails that's interacting with each other. Using what we learned about kinks and then how they interacted within a phospholipid, we should understand the fact that this will be the most fluid-like out of the three examples we have here. Because each kink is pushing the other phospholipid out of the way and making for a more permeable matrix. This one we have a bilayer based off an animal cell. So we have cholesterols, some of them are kinked and some of them are not. Basically, it's going to be fluid-like, but it's also going to be solid-like. It's going to hold its shape, but be permeable and be able to flex and move. In the third example, we have a lipid bilayer with long saturated chains. Using what we learned in the past, long chains means that it's going to interact more with each other and therefore be more solid-like. Also, being more saturated means it's going to be more tightly packed together and also be more so solid-like at room temperature.